The purpose of this lab is to record the motion of an object that is moving at the same speed without changing direction, then to construct a computational model simulating this and compare the results between the two. In this experiment, we had a bottle, this was our system, rolled on a table, and the table, air, force of gravity, and any other force that could have acted upon the bottle being the surroundings. A recording of this was taken and put into Tracker, where the displacement of the bottle was recorded frame by frame over 10 frames, which at 30 frames per second is 1/3 of a second, and observed position versus timetable was created. Here's a screenshot of Tracker with the observed position versus timetable over here. From 0 to 0.1 seconds, the observed position of the bottle and predicted position were essentially the same. However, as time progressed, the observed position became greater than the predicted position at each time interval. As shown by this graph, as time progressed, the observed position in red was greater than the blue, which is the predicted position. Physics ideas used. In this, we use the physics ideas of the average velocity formula, kinematics equations, and Newton's second law. The average velocity formula could be used in this scenario because since the net force acting upon the bottle as it rolled is 0, the average velocity should be equal to the true velocity of the rolling bottle at any point during the observed 10 frames. And to calculate this average velocity, we took the position vector of the bottle from frame 2, then subtracted the position vector from frame 1 from that, then divided that by the change in time to find the average velocity, and in turn just velocity at any time of the rolling bottle. Then these kinematic equations were used in the GlowScript code so the computer could calculate what the velocity of the bottle was at any time, which as we know is constant, but the computer still needs this code to run it, and that is why the average velocity was found to plug in the initial velocity in this computer equation, and then to calculate the position as time progressed of the computational rolling bottle. And also these kinematic equations can be used because force is constant at 0. Newton's second law can be used because mass is constant, and it was used to prove that force divided by mass equals acceleration because this kinematic equation calls for acceleration right here. And then instead of that, we just plugged in force divided by mass. In this, we assume that the net force is constant, mass is constant, the acceleration is constant, and the velocity is constant. This is some screenshots of the computational code. The mass of the bottle was set to the appropriate mass as 0.9072 kilograms. The force acting upon the bottle, as said, is 0, so it was set to that. Here are the two kinematic equations that were discussed in the previous slide. The time observed is set to about 1/3 of a second, and the delta t is set about to 100th of that because you want delta t to be significantly smaller than the observed time. And here's the output of the code. This bullet right here is just reiterating the preview of the results, so we'll just go straight into more in depth. Since we know the computational model shows what should be the position of the bottle at each time interval, and since the observed position became greater as time progressed, this implies the velocity of the bottle increased in the x direction as time progressed from its initial velocity. And here is once again the graph. As you can see, as time progresses, it seems like the red seems to be going faster than the blue, and the red is the observed position, and the blue is the predicted position. And since they start out the same, it looks like red is speeding up compared to blue, which we know blue is constant because it's computational. The fact that the velocity seems to increase as time goes on seems to imply that there could potentially be another force acting upon the rolling bottle that is causing it to speed up. Or it could just be some sort of error. Possible sources of error is that the actual bottle is cylindrical and has dents, while the computational model assumes the bottle to be a perfectly round sphere. Human error could be used in pinpointing the exact middle position of the bottle, causing the position to not be perfectly recorded for each frame, and the surface of the bottle was rolled on could have had bumps on it affecting the rolling of the bottle. If we flipped our x-axis, the only difference would be that the position vector and the velocity vectors would become negative, but their magnitude would stay the same. And the forces seem to be the force of gravity, the normal force of the table, both acting upon the bottle, and the force of air resistant and friction acting upon the bottle, but we're not accounting these two. And since gravity is pushing down and the normal force is pushing up, these cancel out. And here's the glow script code. Thank you.